Subscribe my channel for physics, GE and NEET.
Hello students, good morning all of you. This is our fourth lecture on moving charges and magnetism. In previous videos we are discussing so many concepts according to the Biot-Savart law. But today in this video I want to explain Ampere's law, and you will know about what is the major differences between the Ampere's law and Biot-Savart law. Okay, so let us start our topic. Before going to that, you have to subscribe my channel and like, share to your friends. Thank you. Let us start our topic. This Ampere's law. So what is the Ampere's law? So the Ampere's law is used to find the magnetic field of any closed surface. The magnetic field, the net magnetic field will be found out by the using of the Ampere's law. In our previous session we have discussed how we can find the magnetic field by the using of the Biot-Savart law. So what is the purpose? There is a Biot-Savart law. Still we have to using the Ampere's law. So because of that, the Ampere's law is used to find the net magnetic field at any point from the current carrying conductor. Of course, it is also having same process in the Biot-Savart law. But the variation it is the here we have to find the net magnetic field for the perfect shape of the any other bodies. Okay, so here it is the symmetrical surfaces, but in case of Biot-Savart law we can find the net magnetic field of any irregular surfaces of any shape of the materials. Okay, so this is the symmetric surfaces, and Biot-Savart law will be applicable for the any type of surfaces. Okay, so that is the major difference. You have to find the net magnetic field. And in case of Ampere's law, a current carrying conductor must having the current of steady way. So the steady current will be having the conductor, then we have to use the Ampere's law. But in case of Biot-Savart law it is not. Okay, so that is the possibility of that is the major differences between the Biot-Savart law and the Ampere's law. So what is the Ampere's law here? So let us write the Ampere's law. So the line integral of a magnetic field, the line integral of a magnetic field of a given closed surface is mu naught times of current inside the surface. So this is the Ampere's law. So here in this, the line integral of magnetic field, so that is nothing but B dot dl, which is line integral, circle integral of B dot dl. So it can be says that is circle integral of B dot dl. So the circle integral of B dot dl, it is equal to mu naught times of current inside the surface. Mu naught times of current inside, mu naught times of current inside. So this is the Biot-Savart law. For suppose, so this is a one of the surface we have to assume here. This is the surface, closed surface. So here there are a current which is I1. So this is the outward. A current which is I2. This is the inward. A current I3 which is inward. A current I4 which is outward. A current I5 which is inward. These are the different currents in this surface. Okay, so here we have to find, by the using of the Ampere's law, the net current which is valid for inside the surface. The net current which is valid for inside the surface. So here the outside of the surface, these will not be applicable. These two currents are not valid to find the net current. So which currents are outside of the loop, that currents are not added or not counted. So that is the major we have to remember. And which are the currents are inside of the loop. Which currents are inside of the loop, that currents will be added. Okay. So here the net current, it is, how you can write that, integral of B dot dl, it is equal to mu naught I, it is nothing but, how we can write that, I, where which is the inside, this which is inside, that is positive, which is outside, that is will be taken as negative. So here, whereas I2 and plus I3 and minus of I1. So how we can write that sign here? So I2 is positive because of the current will be inwards. I3 is taken as positive because the current is inwards. I1 is taken as negative, that is outward. Right? So this is the net current, or by the using of the magnetic field in the circuit, in the closed path. Okay. So here, whenever the we have to applicable the Ampere's law, here the direction of the magnetic field and the smallest element dl, the direction of the magnetic field and the small element dl are always in the same direction, So same direction means theta, the angle between them, theta is equal 0. So for suppose this is the dl element and in this direction there is a b. Here the theta, it is equal 0. The theta is equal 0. The angle between b and dl is always 0. Right? But coming to the Biot-Savart law, where the angle between B and DL, it is equal, theta, it is equal 90 degrees here. The angle between B and DL, perpendicular to each other. And also the angle between DL and R is also perpendicular to each other. Okay, so that is the major difference in Ampere's law and Biot-Savart law. So this is Biot-Savart law. Okay. And one more important point, important difference between the Biot-Savart law and the Ampere's law, that is the distance between the point which we have to assume that. Distance between the point which we have to assume. In the Biot-Savart law, the magnetic field is inversely proportional to the square distance. But in case of Biot-Savart law, the magnetic field is directly proportional to the distance of the point which you have to assume. So here it is directly proportional to the 1 by r, right? It is inversely proportional to the r, inversely proportional to the r, or directly proportional 1 by r. Okay, but in case of Biot-Savart law, B is directly proportional 1 by r square or inversely proportional r square. Inversely proportional r square, inversely proportional r. So these are the major differences between the Ampere's law and Biot-Savart law. Okay, so let us see what is the net magnetic field acts due to infinite long bar straight wire. Infinite long bar current carrying straight wire by the Ampere's law. Let us see. So here you have to practice more and more times, then only you have to get the ideas about the Ampere's law and to the Biot-Savart law. So here there is a current carrying conductor which is having infinite length, here. Okay, having the current I. So at this point we have to assume a point P from the r distance. We have to find the dB value, the magnetic field, how much here at the point P. Okay, so here we have to assume at first there is an Ampere surface, Amperian surface. This is the Amperian surface. So the Amperian surface should be in the circle, in the frame of circle. Okay, the radius of r. At this point we have to assume a small element dl, which can have in the magnetic field as same direction. Now according to the Ampere's law, circle integral of B dot dl is equal to mu naught I. Circle integral of B dot dl is equal to mu naught times of the I inside, current inside, where mu naught is the absolute permeability. Mu naught is equal to absolute permeability. And I, it is the current inside of the surface. It means inside of the surface. Where from this we can write that circle integral B dot dl from A dot B is equal to AB cos theta, that is dot product or scalar product. You can write that B dot dl it is equal to B dl cos theta. Since we can write that circle integral of B dl cos theta, it is equal mu naught I, where theta is the angle between B and dl. Angle between B and dl, that is theta is equal 0. Here. Therefore, they are always parallel to each other here. B and dl are parallel to each other. Hence, you can write that circle integral B dot dl it is equal, where cos 0 is equal, since cos 0 is equal 1 here, where it is mu naught I. So then you can write B is outside of the integral and it is dl into mu naught I. So here, if the integral will be possible to dl, then you can find the total circumference of the circle here. The circumference of the circle, it is B into 2 pi r, it is equal to mu naught I, where you need to find B only, then mu naught I by 2 pi r. So this is the magnetic field net magnetic field of a infinite current carrying straight wire. Infinite current carrying straight wire. Due to the Ampere's law. Due to the Ampere's law. In case of Biot-Savart law, already we seen that B it is equal, that is, what is that here? Mu naught by 4 pi I into 2 pi r by r square. 2 pi r by r square, where r and square will be cancelled, pi and pi cancelled, 2 and 2 times it is mu naught I by 2r. Mu naught I by 2r. So this is the circular coil. This is the circular coil. You should not be confused. You should not confuse. It is for circular, the center of the circular coil, how much magnetic field according to the Biot-Savart law. It is 2r only. This is 2 pi r. So this is the straight wire. This is the straight wire. Okay. And this is the circular wire. Circular current carrying wire. At the center of the circular current carrying wire, how much net magnetic field? That was mu naught I by 2r. So this is the mu naught I by 2 pi r, that is straight wire. That is the straight wire. Okay. Right. So this is the variations between the Ampere's law and to the Biot-Savart law. So if you like this video, please share to your friends and like, and do not forget to subscribe my channel. Now let us see one application. So which is to find the line integral of a given surface. How we can find the line integral of given surface? By the using of Ampere's law. Line integral means it is belongs to the Ampere's law. Okay. So here there is so it is the surface here, a surface enclosed. It is the closed surface. Here there are currents are there. That is I1, I2, I3, I5, I4, okay, I6, I7 and I8. Right? So there are 8 currents are there, 8 wires are there here. So find line integral that is B dot dl for the given loop. For the given loop. How we can find? So by the according to Ampere's law, you can write that line integral B dot dl, it is equal mu naught times of I, that is inside. You have to remember this one, I inside. So which currents are inside the loop is only valid. So remaining all the currents outside the loop are not valid. So this is not valid. I4, I6, I7 are not valid. I4, I6, I7 are outside of the loop. Hence they are neglect. So remaining wires are inside of the loop, that is I1, I2, I3, I5, I8. Okay. Now let us write. So circle integral B dot dl, it is equal mu naught into, whereas I inside it is minus I1, because of this is the outward. So this symbol is inward. Inward gives the positive sign, outward gives the negative sign, and plus of I3 and plus of I5 and plus of minus of I8. Okay, so this is the line integral in this loop. For suppose each wire has current I naught. Each wire has the current I naught. So then the line integral, it is equal to mu naught into minus I naught plus I naught plus I naught plus I naught minus I naught. Okay, here plus I naught minus I naught minus I naught plus I naught cancel. Remaining, that is only I naught. It is mu naught I naught, that is circle integral line integral b dot dl. So this is the line integral b dot dl in this case. Okay, right? So this is the line integral of this given loop. Clear? Right. Now the application 2. Find the magnetic field of a hollow cylinder. Radius r at inside and outside of the loop. Find the magnetic field of a hollow cylinder radius r at inside and outside of the loop. So here this is a cylinder. Which is hollow cylinder, which has hollow. Okay. So here you need to find the inside of the cylinder, how much magnetic field it consisting, and outside of the loop, outside of the cylinder, how much magnetic field consisting. Inside of the cylinder means here there is a point, you have to guess inside of the cylinder, that is point P. And outside of the cylinder, here you have to find at point Q, you have to find the magnetic field. Okay, let us. So this is the inside. Just I have to find the inside of the cylinder. Inside B. We have to find the inside B. Inside magnetic field. Okay, right. So here there is a view which you can assume that the top view of the top view. So let us write top view. So this is the cylinder. Here there is a cylinder. We have to see in the top view, right? So there is here. This is the cylinder. The top view of the cylinder here I drawn. So this is the current which is passes outward, in this direction. It is in this direction. It is the current. So outward direction. And here there is a cylinder. We have to see from the top view in this direction. Top view. So at this point we have to assume a point P. It is the inside of the cylinder. So this is the cylinder we have to assume here. This is the cylinder. Okay. Inside of the cylinder there is a point P. At first it has the radius capital R. Okay. So at point P you have to assume the Amperian loop. So this is the Amperian loop. Amperian loop here. So the Amperian loop has the radius, it is smaller. right? So here in this condition, small r is less than capital R. Small r is less than capital R. Small r is the radius of the Amperean loop, and r it is the major loop which you have to cylinder loop, right? So there is inside, there is no current here. So by the Ampere's law you have to write that B dot dl it is equal to mu naught times of I inside. I inside. So inside there is no current because of it has hollow cylinder. Inside there is no current. No current locates at inside. At inside. It is I inside is equal to 0. Hence, you can write integral B dot dl it is equal to 0. Something into 0, 0. B into circle integral dl it is equal to 0. B is equal 0. So here the magnetic field at inside is equal 0. At inside is equal 0. Okay. Now coming to the outside. So that is the second case. That is outside of the cylinder. Outside B. So here there is a point. This is the main loop of the cylinder. Here there is a point Q here. The radius at first it is the capital R, and here from this point our assuming point it is the Q having the radius small r. At this case small r is greater than capital R. Small r is greater than this one because of the point always be outside of the loop. The point which is we have to find the magnetic field, that will be locates always outside of the loop. Hence the distance is more than to the radius of the loop. Okay. So here from the Ampere's law, B dot dl it is equal, integral B dot dl is equal mu naught times of I inside here. Okay. So here you can find that there is B circle integral of dl cos theta, where it is here there is a Gaussian or it is Amperean loop. Here this is the dl and there is the B. So these are having the angle theta is equal to 0. Hence you can find that B integral dl it is equal to mu naught I, where cos theta is equal to 0. Cos 0 is equal to 1. Okay. So B integral of dl, that is nothing but the dl elements will be always gives us the integration of circumference of the circle. So that is the 2 pi r. 2 pi r here it is mu naught I. So B it is equal to mu naught I by 2 pi r. 2 pi r. So this is the magnetic field at outside of the loop. Clear? At outside of the loop which has the radius smaller. Which has the distance of the smaller. Right? So this is the condition we have to find the in case of hollow sphere the net magnetic field by the using of the Ampere's circuital law. Okay.